we will move on to organic question very quickly. So you have given isomers of methylpentene. So methylpentene means you should have like a 5-carbon chain like this. So you have a 5-carbon chain, and there should be a substituent methyl group. Okay. And A and B are structural isomers. Okay. A and B are structural isomers. And the molecular formula is given C6H12. So the first thing that I always tell you, identify the formula. This is C6H12, which means this is a CnH2n group. So which is very essential to identify. Here there should be a double bond. Okay. And it verifies this because A exhibits geometrical isomerism while B exhibits optical isomerism. So you need to understand there is a clear difference in the place where this double bond can be. Okay, because A shows geometry. So think about a structure of the methylpentene. Okay, so there should be a pentane linear chain. There should be a double bond somewhere. For an example, if I put the double bond here, so I can arrange this one as CH3. Now this carbon has the same CH3 group, so it cannot be a arrangement which it shows geometric isomerism. So I have to shift this double bond based on the structure. Okay, so B exhibit optical isomerism. There is another point that they have given. And on hydrogenation, A and B yields the same compound C. So this is type of a question that we have already discussed before also. We give the same compound when we do some difference. Okay, with the molecular formula. Now this has become basically an alkane. And C does not exhibit optical isomerism. So it does not show optical isomerism, because it should be a fact, because C should basically come from mainly A or either B, because those two will give the same compound. And you need to draw the structures. So you need to draw the structures. And then they have given, using A and B, you need to predict what are the products that is going to form here. Okay. So we will see how it goes. So I will stop the screen for a while. Okay, so we'll start. Right, so we have C6H12. Right, so A shows geometrical and B shows optical. And when you do the catalytic hydrogenation, it will give the same compound C. So first we will try to obtain the optical one, or maybe you can use both, either optical or the geometric one. Okay, so we will first try to identify one. So let's see, we have the CH3 group like this, and another CH2, CH3. So we have 1, 2, 3 carbons here. Another one is 4 here. And I can use the double bond like this. So 1, 2, 3, 4, 5 penta, and I have a methyl substituent, and I have a double bond here, which is not showing geometrical isomerism in this case, because there is 2 similar groups here. But here, this shows optical isomerism. Okay. Typically, this can be the most acceptable one for the optical isomerism. And then we will try with the geometrical one. So basically, there should be 2 different groups here in the carbon. Let's say it is hydrogen, for an example, right? Hydrogen. And then here you need to put another 3 carbons principally. So here I can put like CH2, CH3, and here 1, 2, 3, 4, 5 CH3. Okay. Now this is acceptable if methyl group is not a substituent. For an example here 1, 2, 3, 4, 5, and methyl is a substituent which make this as methyl pentene. There is should be 6 carbon. Now here there is 1, 2, 3, 4, 5. So there should be another carbon that is going to be added to this structure. So basically what can I do here? I can just make this as CH3, right? And this is the transform of this structure. So the cis form can be drawn like this: CH3, CH3, and there is hydrogen here, and there is CH2, CH3. Okay. This is one form of the structure. Now we will try to do the catalytic hydrogenation. So you can understand why this was not there. If I take hydrogen as the cis and trans group for the double bonded carbons, this cannot be because there should be 6 carbons, which should give the methyl substituent. In fact, you can use here as CH2, CH3, there is no problem. But when you now do the catalytic hydrogenation, now this will not give the same product because there is no methyl substituent here. It's only a linear hexane chain. So there is a problem. So that is why I kept this as CH3 and I changed this as CH3 to make it a substituent, methyl substituent. Okay. So in principle, now you have this compound and this compound. Now this is the cis form, this is the trans form. Okay. Now when you do the catalytic hydrogenation of this one and this one, so when you do the catalytic hydrogenation, this part will be converted to a CH2, CH3, which is common to this part as well. And now this C compound does not show geometric isomerism because our question, it says C does not exhibit optical isomerism. Okay, so even it does not exhibit optical isomerism. So this part will be converted to CH2, CH3, which is, there is no optical isomerism now because these two parts are same. And here also when you do the catalytic hydrogenation, it will give CH3 and there will be CH2, then there is the methyl substituent and CH2, CH3. Primarily, it is the same compound that is you are going to obtain here. Okay, so it gives you the idea A, which shows the geometrical isomerism, it should be this one, and B, which shows the optical isomerism, is this one. And when you do the catalytic hydrogenation of these two, which gives the compound this, which is C. And now you understand why it cannot be two hydrogens, because there should be additional methyl group that you have to add here either. But when you add here, when you do the catalytic hydrogenation, there is no substituent. It will be only a hexane chain. That is one point. And the other one is when you add CH2, CH3, this is just a linear chain. There will be no methyl substituent that is added. Okay. So try to figure out that thing here. That is essential to know. Right. So we have A and we have B as well. Now we will see what are the reaction conditions that they have given here for these two compounds. And see this. Okay, now we will check. Now, what they are doing here is they are reacting A and B separately, first with HBr, but in the peroxide medium. H2O2 is peroxide medium. And they obtain D and G. and then they are reacting this with this is A, this is B, and then they are reacting with this aqueous KOH, which is going to give E and F, E and H. In fact, then you add PCC, which will give F and I. So we will start. So this is our compound B basically. This is compound A. So when you add HBr peroxide, what is going to happen? When you add HBr, normally according to the Markovnikov rule, the hydrogen will be added to the most hydrogenated carbon. So this is this. But when you have peroxide, it will happen in the reverse order, the anti-Markovnikov rule. So basically there will be no double bond here, that is acceptable. And here there will be the bromine, and here there will be the H. This one. And for this one, it is again same. There is hydrogen here, so there will be bromine here, and there will be hydrogen here. And then they are adding aqueous KOH. So when you add aqueous KOH, this will be converted to OH. No problem in that. And then you add PCC. So PCC, you know, pyridinium chlorochromate is oxidizing agent, but it is not effective as KMnO4. So if you have a primary alcohol, it will be oxidized to aldehyde, secondary alcohol to other ketone. And if you have a primary alcohol with KMnO4, it will go up to carboxylic acid, as you can remember. So here you can see there is a primary alcohol. So when you add PCC, automatically now this will be converted to a aldehyde. And here, this will be now converted to a ketone, which is this CH3 group. This will be a CO, and there is CH, substituent, CH2, CH3. Okay. And this is from A, it gives F, and this is from B, which it gives I. So clearly you can see we have obtained at the end of this reaction pathway, one is a ketone and the other one is an aldehyde. So this is what they have tested again in the next part. See. So here we have drawn A, B, and C, and we have identified all these structures up to now. And see, give a chemical test with the relevant observations to distinguish between F and I. So you have to distinguish between F and I. So F and I means between ketone and aldehyde. So the easiest way to identify the ketone and aldehyde is the tolerance test, right? So you can identify F and I separately distinguished by using the tolerance test. And compound E is a structural isomerism, isomer of H. So what is compound E? So compound E is the aqueous form, which means the alcoholic form that form from A. So here this is A, which form the alcohol. Here they say it is a structural isomerism. See here, structural isomerism that is found between these two compounds. So what is the structural? So E and H. What is E here? This one. What is H here? This one. So primarily E and H, they are asking about the OH group. So you can see this E is a primary alcohol and H is a secondary alcohol. So what is the difference between these two? The position of the OH is changed, right? In the E, in the primary alcohol, the OH is at the first carbon, the terminal. It was here, right? Okay, if I stop sharing, then you can see. In the second case, the OH is here. What is the difference? What is the relationship between these two? The position of the OH is not changed or changed, or the chain is different or not, or the functional group is different or not. These are the three things that you need to understand when you're comparing, right? So you know in the isomerism part, when the stereo and normal constitutional isomerism is considered, so you consider about the position, chain, functional group. So here functional group is same, OH, alcohol, chain is same, only the position is different with the alcohol, right? So here the position is now here is in the first, and here this is in a different position. So what is the relationship? This is the relationship that they are asking. So name the type of structural isomerism or constitutional isomerism. So what is this relationship? It is the positional isomerism. Okay. And right, so this is another straightforward question that we normally see in structured essay parts, that you have to predict the major product as well as the mechanism. So here there is a double bond between carbon, hydrogen. So you add Br to CCl4. So this is the many common reactions that we see here. So there will be 2 Brs added here. So there will be the dipyroma product, which is the major product. And the reaction type, so if you remember, this is started with the bromonium ion. So basically the pi bond attacks one Br. So Br is positive here. So this is an electrophilic addition. Okay. Don't forget, this is an electrophilic addition. This is a AE mechanism. Okay. And you have a benzaldehyde. This is benzaldehyde. So you add CH3COCl. So benzene compounds always, you know, they tend to go with the substitution reaction. And as well as since the benzene, the phenyl group is positive, electron deficient compound. So it goes to electrophilic substitution. And ROH will be reacting with PCl3 to form RCl, which is nucleophilic substitution. And when you have an alcohol, you add either conc H2SO4 or anhydrous Al2O3, and then you heat. So you will have the dehydration of alcohol, which is dehydration, the water is removed. So basically this is a elimination reaction. And finally, when you have a Grignard, so R will be in minus charge. So this will be added to the carbonyl carbon. So positively charged carbonyl carbon. So R minus is the nucleophile, and this is added. So this is a nucleophilic addition reaction. Okay, AN reaction. And the major product that when you have this addition is there will be the R group on the carbon, and there will be O minus and MgBr that is attached. You cannot draw the alcohol here because to get the alcohol you need another step. This is just the first step. In the second step, if you add H plus H2O, there will be this second step happening, formation of the alcohol. Okay, so this is very straightforward. And the second thing is they are asking about the second reaction. So this is very common reaction. First you have to show the formation of the CH3 in primarily what is forming here. There will be CH3 CO, there will be plus here, and there will be Al Cl4. You can show this formation of this. The reaction between CH3COCl plus AlCl3 will form this. Okay, there will be a minus charge basically here. And then you have the benzene ring that is going to attack. Okay, so there will be the double bond here and here. And this is going to attack here like this. And this bond is going to break like this. Okay, so there will be the reaction that is happening. Okay, so you can show the mechanism. But make sure when you are writing mechanisms, you have to indicate all the species that is present in the reaction. You cannot drop. For an example, when you give the product of this, there will be benzene, the COCH3 is attached. Plus, you need to show this AlCl4 minus. If you did not show this AlCl4 minus, marks will be reduced. Okay, so this is a straightforward reaction. We commonly discuss this in the theory class also. Not much of a case, okay?